Good morning. We are very happy to have today two speakers. And the first talk is the talk by Tomasz Downarowicz. And the title is Rauzy's Approach to Determinism. Please.
Okay. Thank you very much. Let me hide this. Hide this here. Oh, okay. Thank you very much for the invitation. I am very happy to be here again after a longer break. And I would like to present the results of my joint work with Vitaly Bergeson. We have a joint grant, Harmonia from NCN, and we visit each other quite regularly in the recent years. What I'm going to present is part of our joint work. We have several other papers. This is going to be probably the third paper, and there are two more in progress. So it's really a very fruitful work and collaboration. And Vitaly is interested in the notion of determinism. So the title of the talk is Determinism, and this time it is about Rauzy's approach to determinism. Maybe we'll find it. Maybe we'll find. But are the online participants still?
Yes, we still here.
Okay. Fine. Okay, so okay, we fix an integer that will be a base of our expansion, and we call the normal a number normal. This is well, I'm not discovering anything new. Is a number. Number normal, this is well, I'm not discovering anything new. Is a number is normal in base B if the frequencies of blocks are exactly measured. So if you want to use ergodic theorem, you can use the law of large numbers, which is more elementary. All right, thank you. That we know all that Lebesgue almost all numbers are normal. Okay, so in general, we have a more general approach. We have a dynamical system, and we have an invariant measure on that system. This is a topological system, so it's a compact space and a homeomorphism, or actually continuous map, because we will be talking about one-sided shift or 2x mod 1 or bx mod 1. So in general, we say that the point quasi-generates the measure if the sequence of averages, the narrow averages, converges weakly star to mu along some subsequence. If this happens for a sequence, then we say that any measure of changing the point at each case, then you still get an invariant measure. One thing, every time compactness is at least one measure. So the set of quasi-generated measure is never empty, and measures which I denote. It is also known that it's quite connected, but we won't be using this. And it is a one. It's a singleton if and only if the point is generic for Okay, so what means that a point is called by the pointers to any dynamical system. In any dynamical system, you can look for deterministic points. So all measures quasi-generated by the point should have entropy 0. We mean the Kolmogorov-Sinai entropy function. Okay. So what means that a number is deterministic? We have to fix that base still, so we have a base B, and the number is deterministic if, well, you can truncate the number, reduce it to the fractional part, because the frequency depends only on the infinite part of the expansion, and you look at the gamma, which is 0, 1 modulo 1. And you look at the transformation bx mod 1, and you say that the number is deterministic if it is deterministic in this system. Equivalently, use deterministic under the strict transformation. This is what Benji Weiss calls completely deterministic, and because we don't use any other, the point is deterministic. Okay. So what was done on the so the first result of this kind was by Wall, who proved in his thesis that if you have to skip 9 by that, by Wall, who proved in his thesis, if you have normal in base B, you get K with step M, and we if you read along an arithmetic progression, it's still normal. And later, Benji Weiss and Tetsuro Kamae asked the question, what other sequences other than arithmetic progressions have this problem? And they proved that an essential increasing sequence of natural numbers preserves normality, which means exactly this, that if you take a normal number, any normal number, and look at the digits along the subsequence S, then you also get a normal number. What's crucial here, and they normal numbers. So if you all any infinite subsequence, you still have an IID sequence of random variables. So almost sequences, because we call such this characterization sequence deterministic also. When its characteristic function is deterministic under the shift, then we call this set of natural numbers deterministic. Among deterministic subsets, there are subsets of density 0, because they generate only one measure, trivial measure, concentrated at the fixed point 0. And such sequences of 0 density never preserve normality, because you can take a normal sequence, change it along the density 0 subsequence, say, put zeros everywhere there. And this subsequence will consist of zeros, while you have not destroyed normality of the original point. So you have a normal point whose subsequence is not normal. So you need to assume this essentiality. Okay. So this is an interesting interplay between determinism and normality. I will comment on this a little later, what this is about. But now let me summarize what Rauzy proved in terms of interplay of normality preservation. He proved a different sort of normality preservation, some kind of algebraic normality preservation, and here he does not need to assume essentiality. So here is a theorem by Rauzy. A number y is deterministic in base B if and only if for any normal number in base B, the sum, the algebraic sum of numbers. It's not the sum of symbolic sequences coordinate-wise modulo the number of symbols or something like that. If you do that, you have to remember that there is a carry forward, right? If you start adding two numbers, you do the usual addition in base B of numbers. And so here is the result of Rauzy, very nice. It's a different kind of normality preservation. It's normality preservation by addition. A number is deterministic if it preserves normality by addition. And we looked at this proof, and it's quite interesting actually, because Rauzy proves it using some combinatorial properties of deterministic sequences. Roughly speaking, I'm not going to talk about it in more details, but he has this observation that a number is deterministic, and this is actually the source of the notion of the terminology determinism. If we know it from ergodic theory very well, but he has a combinatorial approach, very interesting, using codes and optimizing the codes. So roughly speaking, if we know sufficiently many digits following the nth digit in the expansion of y, then with high probability we can predict the missing digit. In other words, if you know the tail of the expansion, you can fill it up, the missing initial terms. That's what determinism is about. And we know it very well that if you have a zero entropy system, symbolic system, then knowing the past, we can predict.
But what's interesting here is this accuracy, because we know it for a certain measure, right?
Right.
And what does it mean by accuracy?
No, this is my maybe not precise, but so what he does is quite interesting. Maybe I will say it in 2 words. He takes all possible codes, by which I mean like a vocabulary. You take a long block of some length n, and to each block you associate one symbol. That's what I call a block code. And then he takes all such block codes and he tests each of them along the sequence. Namely, how often does the sequence obey that code in terms of symbols from n+1 to n+k, where k is the length of the code? How often does the image of that code agree with the nth symbol? And he does the statistics for all possible codes, and then he takes the supremum, or he takes the error and the infimum. And the sequence is deterministic if with the length of the code you get a 0 as the infimum. So this is the predictability. So for a fixed number n, or k actually, yeah, k is the sufficiently many digits. That's k. So for large k, you can predict this number with high frequency. Okay. So he uses this criterion to prove the theorem 2, to prove this normality preservation by addition. And you can imagine that the proof is quite complicated, because this criterion for normality is very technical. So we looked at this with Vitaly, and we discovered that this can be proved in a very short manner, just using ergodic theory. So I make this comment here to remember to discuss with you this issue. So I will come back later to this. If I forgot, keep in mind. So I keep going. So here is a short proof of one direction of Rauzy's theorem using just the entropy and joint. So elementary tools from ergodic theory. We will prove that if X is normal and Y deterministic, then the sum is normal. This is almost trivial if you look at it. So let Nk be an increasing sequence of natural numbers along which X plus Y quasi-generates some measure. What we want to prove is that this measure is lambda, that it's normal. So we can assume that along the same subsequence, this pair of sequences, X plus Y, when I talk about sequences, I mean the expansion, almost the BR expansion, and Y quasi-generates some measure psi. Actually, this is not about sequences. You don't need to refer to sequences. You can look at the action on the circle given by BR mod 1. So you take this pair, and on some subsequence of that sequence, it always quasi-generates something. So it generates, this pair generates something under the action of the product action. Okay. And psi is a joining of nu, because on the first coordinate we have assumed that X plus Y quasi-generates psi. X plus Y generates nu, and Y is some measure. It's a projection of psi on the second coordinate, but mu is obviously quasi-generated by Y. And Y is by assumption deterministic. So the entropy of mu with respect to R is 0. So then you have to know a formula for entropy of a product of a joining. Psi is a joining. So the entropy of the joining is less than or equal to the sum of the entropy of the joint measures, but this term is 0, so it is H nu of R. And actually, you know also that this entropy is bigger than or equal. So it's actually equal, but we don't need this other inequality. Now look at the mapping on the square, Cartesian square of the torus. S sub t goes to S minus t modulo 1. And this is a factor, topological factor from the product from the square to one coordinate. Because this mapping is obviously continuous and commutes with the multiplication by b. And it maps this pair to x, because x plus y minus y is x. So it sort of reverses the process of adding y to x. And so by a simple argument, it maps this joining to the Lebesgue measure, because x is normal by assumption. Whatever x quasi-generates, it must be lambda. Okay, so of course a factor has larger entropy than, the extension has larger entropy than the factor. So we have that this entropy is at least log of b, which is the entropy of the Lebesgue measure under the mapping R. And we have just proved on the previous page that this is less than H nu of R, and actually we know that it's equal, so we get this. And now we are using one standard fact that the Lebesgue measure is the unique measure of maximum entropy under the action Bx mod 1. So that means that that whenever x plus y quasi-generates something, this something is the Lebesgue measure. So that means that there is only one measure quasi-generated, which, as we earlier noticed, means that x plus y is generic for lambda, so it is not. So very simple proof using just joinings and entropy and the uniqueness of measure of maximal entropy of that part. Now, the other direction of Rauzy's proof, we don't have a simpler proof. Rauzy's proof of the other direction, which says that if a point has the property that it preserves normality under addition, then that point is deterministic. This proof uses, well, in some sense, Fourier analysis. You have to look at the expansion and functions, and you prove actually this. And we don't know any simpler proof. Nevertheless, we have some generalization. But now let me go back to this comment here. To this comment. So we have this phenomenon that determinism is the same as preservation of normality. And we know it in two senses. Preservation of normality along a subsequence, the subsequence has to be essential though, or preservation of normality by addition. Here we don't need anything. So one may ask, and actually we asked ourselves, the following question: is this about disjointness, or is this about entropy? Because in the case of deterministic and normal, you have both things. You observe that both the disjointness and entropy relations are satisfied. And what is disjointness? We know very well that any measure of entropy is zero, and the Lebesgue measure, which is for that transformation a Bernoulli measure, are disjoint in the sense of percentile. And this disjointness, if you think about it for a while, what does it mean? It means that any joining is actually the product joining. So the frequencies of pairs are products of frequencies of each. So if you have a pair of blocks, and you look how often this pair of blocks appears in the pair of sequences, you have to just multiply the frequencies here and here. And in this way, you can prove many things about the relations between deterministic sequences and normality. So you can think that whenever you have disjointness, you have some similar phenomenon. The other phenomenon is just entropy. You have entropy zero, that's deterministic, and you have maximal entropy, that's normal. And if you combine these two, you cannot get anything else than, again, the maximal entropy, because you're adding or subtracting entropy zero. So the other entropy remains, and because this other entropy is maximal, you know exactly what measure you generate, because there is only one to choose from. So okay, so we have with another author, we have a very interesting observation about the disjointness, and it turns out that disjointness is insufficient. We thought that, okay, not only Bernoulli measures are disjoint from zero entropy, but also all measures with completely positive entropy, which in the invertible case is the K-sigma, the Kolmogorov property. But in one-sided non-invertible case, we call it completely positive entropy. All partitions have entropy zero, or all factors have entropy zero.
And positive.
Completely positive. Completely positive. What did I say?
Factors have positive.
What did I say?
Zero.
Oh, I meant positive. Okay, so what we discovered with Adam Abrams, who now works in our institute, is that no, that is not true for any completely positive entropy system or measure. If you replace in this whole argument Bernoulli measure by completely positive entropy, unless this completely positive entropy is exactly IID, which is Bernoulli, but not only isomorphic to Bernoulli, that's not enough. It has to be purely Bernoulli, so an IID process. Only then you have entropy preservation by deterministic sequences along subsequence. We looked at this Kamal-Weiss type of normality preservation. So what we proved is that unless your completely positive entropy system is purely Bernoulli, then not only deterministic sequences do not preserve entropy, they destroy preserve normality. They destroy normality. For example, you can take the continued fraction business and the Gauss measure. This is actually completely positive entropy. And if you look at the expansion with respect to continued fraction, and you choose, this was actually observed by Hirsing and Van der Heijden. If you and you choose every second digit in the continued fraction expansion. Here you have a countable output. It's not finite. You take every second digit and you squeeze them together and you have some expansion. And you look at the number that you've gotten. This is never going to be generic for the Gauss measure. If the original point was generic for the Gauss measure, which is almost surely true, then the every other term business will never be generic for. And we generalize this with Adam to any deterministic subsequence. So deterministic subsequence not only does not preserve CPE normality, but it destroys it. If you start with a point which is generic for your CPE measure, and you choose the subsequence along some a priori selected deterministic sequence with positive entropy, with positive lower density, then you will never get a sequence which is generic for this for your CPE measure. That's very curious. But here, this jointness works not in favor but against normality preservation. So this is okay. But as far as entropy is concerned, the things are more optimistic, and this is what we have proved with Vitali in this aspect. Okay, so we have to define something which we call lower and upper entropy of a number or of a sequence. Simply, you take all measures quasi-generated by that element x, and you take the infimum of the entropies, and you take the supremum of the entropies. If these two agree, then we say that the point has entropy, and we call it h of x. So determinism and normality are instances of this upper and lower entropy. Namely, the point is deterministic if the upper entropy is 0, and point is normal in some base if its lower entropy is a maximal value. Or in the symbolic case, it is you can talk about this for numbers and for symbolic sequences. It's roughly the same thing. Okay. So using the same methods, just joinings and entropy, we can prove the following: that for any two numbers in the circle, you have this crazy inequalities, A, B, C, D. There are 4 inequalities. The first inequalities estimate the lower entropy of the sum, and the second pair of inequalities estimate the upper entropy of the sum. And if you want to look at it, it's of course must be positive, but otherwise you take the difference between the lower entropy of one number and the upper entropy of the other number, and the other way around. And you cannot put the absolute value here because you reach also the lower and upper mark. And from above, it is majorized by log of r. That's obvious. And otherwise, you have the sum of these two. But you need to switch the bars also. It's curious, a little bit complicated, but this is the best we can do, and this is actually true. You can show that you cannot include this. Then if you look at the upper entropy of the sum, below you have the absolute value of the difference of either the lower entropies or the upper entropies. Which one is bigger, that one wins. And for the upper estimate, you have to take the sum of the upper entropies. The lower entropies do not play here. And log of r is, of course, an obvious bound. So it's a little complicated. Maybe let's not focus on that too much. But what happens when y is deterministic? Well, then both lower and upper entropy of y are 0. So you can immediately see what happens. These formulas simplify a lot. The lower entropy of the sum is the same as the lower entropy of x, and the upper entropy of the sum is the same as the upper entropy. And you prove it exactly using the same methods, except you have to play with the sequences a little more, choose subsequences for which more things converge to some values. So if you now choose x to be either normal or deterministic, you will see that both properties are preserved by deterministic sequences by addition. Okay. Here is an interesting observation also, that we don't think anyone made before us. Although people have considered deterministic numbers, they were always considered in some fixed base. Turns out that the base does not play any role. If a number is deterministic in one base, it is deterministic in any other base. And the proof is just one line. Simply, that you consider two mappings. One is given by bx mod 1, and the other one is cx mod 1. You have two bases. And because the bases are integers, there is a common multiple of b and c. So you can take r to the power c and s to the power b, they are the same. And we call it t. So you can easily prove that the upper entropy with respect to r is 0. That implies that the upper entropy with respect to t is 0. And that implies that the upper entropy with respect to s is also 0. You just play with the power rule for entropy. That's basically the same. So it's a striking, very simple result, but it frees us from specifying the base for deterministic numbers. However, you have to remember that normality does depend on base. And Bill Mans is a specialist in this business. He has lots of examples where numbers are normal in one base, but not in the other. He knows how big set of such numbers that are normal for one base and the other is not. How large these sets are depending on the relation between the two bases.
Isn't there also a result by Host?
There was, yes. Bill bombarded me with a number of references for this fact, but the only thing we need for now is to know that determinism is different in this aspect from normality. But this is because entropy 0 is in that sense universal, and maximal entropy depends on how many symbols you have. So this is obviously a different story. Okay. But what we have focused on with Vitali and where we think things are more interesting. So this was sort of this part so far was just reproving Rauzy's results using some more elegant maybe proofs. But what we found really interesting is to look at a different operation, different algebraic operation, multiplication. And it has been known, it was even, I think, in Wall's dissertation, that multiplication by a rational number preserves normality in the term. So if you multiply a number by a rational and your number was normal, then the product is also normal. Or if your number was deterministic, the product is deterministic. And we can also prove it the same thing using our factors and joinings method. Namely, if you multiply a number by a rational, of course, non-zero rational, then you preserve the lower and upper entropy of that number. And the proof is very simple also. You look at the mapping that sets x to nx, and you find out that this is a finite to one topological factor map from our system the circle with the dx mod 1 to itself. And because finite to one factors preserves entropy of matter, then you have to have uncountable to one to change the entropy. Even countable to one is the preserving the entropy. This easily implies that if you take the entropy of nx, lower and upper, you get the same value. And then you replace x by x over n, and then you get this. And combining these two results, you can get any rational. Okay, so this is known. We have a nice proof, and what do we do next with it? Well, maybe numbers preserves normality. Maybe multiplication by deterministic number preserves normality. So this is what I just said. Perhaps these theorems suggest upper entropy, normality, maybe determinism. This, however, is not. And we have examples, and for the remaining couple minutes, I will show you the examples. The part deterministic. So the x normal in base 2 between the deterministic number. If the number was if the number y was maybe happens on the residual was one single count talking about blocks on two symbols all the time now. So there's two to n of these blocks, and then any two successive blocks different from one place. And where you start changing occurs only after all passing under the name of code gray. Code exists in the literature, nothing new, but we modify it a little bit because of our choice. But you don't apply any carry, right? And in this way, you have these properties. And then we have to modify these code gray or this ordering by mirroring all the negation. Then this sequence is a bit, so they differ at all n positions. That in this ordering, that this either both mirror or none of them was mirror. If you start with a B3, for example. The concatenation of all blocks in the of order K in this funny ordering that we discussed before. It's the gray code with then mirroring every other block. So you do this, and you have defined B1 sub K, but at the same time B2 sub. Still distracting. So you also define B2, B3, and so on for the order K, but you also define B1 sub K. So eventually, only the blocks B with the lower index 1 are important for us. K is the prefix of B1 sub K plus 1, so these blocks converge to an infinite sequence. And if you take the infinite sequence, this is going to be our X. Oh, I wrote it in a funny way, but this is what it is. You take the blocks B1, they are longer and longer, and they are expansions of the previous one. So they converge to something. And here is the beginning of our expansion of the number A. It starts with this block 0, 1, which is here. Then, if you look carefully, this is the funny order of blocks of length 2. The gray code, but starting from 0, 1, with mirroring the second and fourth. So this is some funny thing. And this concatenation then becomes your B1 superscript 2. And then you can work it out to see what B sub 2 is and so on. And you concatenate these guys, remembering to mirror the even ones. So this is a little bit complicated, but this is what it looks like. And you have to take how many? 2048 of the blocks of order 2 to compose the first block of order 3, because 8 to power 2 to 8 is 2048. Okay, so the proposition is that what we just constructed is normal in base 2. I will skip that. The main part is that if you take the concatenation of an ordering of 0, 1 to n, then it is approximately normal. Because all blocks appear there, you have concatenation of all possible blocks of given length, so you have good frequencies of shorter blocks, maybe of orders square root of n. This is roughly how it works, but it's not that easy because the length of these blocks grow enormously fast, and you have some stopping times. It has to be generic, not just quasi-generic. for the newly measured. So you have to be able to prove that if you cut it in some random place, not exactly at the end of B sub k something, then you also have good frequencies, and this is tricky, but can be done. Okay. Now, once we have constructed the normal number, it's time to construct the deterministic number. And this one is much easier to describe. You take so-called IP star set. Actually, the set of finite sums of the sequence NK. So it starts with 0. We have to include 0. That means you will have one digit before the decimal dot, but it doesn't matter. So then you take n1, then n2, then the sum, then n3, then n3 plus n1, n3 plus n2, n3 plus n1 plus n2 plus n1, and then n4 and so on. So this is the set of finite sums, well known in Rauzy theory, for example. So here is what this sequence looks like. It starts with 0, then we have n1, which is 2, n2, which is 8. This is n1 plus n2. This is n3, I mentioned before. This is n3 plus n1 plus n2, and n3 plus n1 plus n2. And n4 I skipped writing because it takes several hundred digits. So it's 2048 times 2 to the power 2048. So we can imagine that it takes several hundred digits to write. Impossible. Okay. And now, once we have the sequence, we just take the set such that the characteristic function, we take the characteristic function of this set and tell that this is the expansion of our y. So what is y? Y has digits 1 exactly at the elements of the set. So it starts with 1 at the coordinate 0. This is why I have included the decimal dot. But it doesn't matter. For multiplication, we don't care if we have numbers from gamma or if we have real numbers. We actually, for multiplication business, it is sometimes more convenient to think of numbers on the real line rather than on the circle. Okay, and then 1 at position 2, then 8, 10, then a lot of zeros, and then you have the same pattern that you had before. So you can see that this y is in some sense almost periodic. You have very nice periodicity structure. You repeat these 2038 zeros again here, and again many times, and then there will be a much larger gap. And everything that you started with will be repeated again and again and again a number of times. So this number is trivially deterministic because you can see with your naked eye that the frequency of it is 1 and 0. So it is trivially deterministic, which is in some sense a little disappointing. Because, for example, in Kamaev-Weiss's theorem, we require that the deterministic number has positive density. But we can improve this example in a very simple way so that your y will have density 1/2. Simply multiply this number by 4/3, which is rational, so you don't lose any properties. Normality is preserved by multiplication by rational. And if you multiply this number by 2/3, you get something which has a very regular structure with a 0, 1, 0, 1, 0, 1 most of the time. So I skip that. The phenomenon is more interesting for this. Okay, so not only it is deterministic for trivial reasons like frequency 0, but it also is almost periodic, so it has very low linear complexity. It's very, very deterministic. Okay, and the proposition that the product xy is again deterministic, which is the miracle that. Okay. What is the idea of how much time do I have? Oh. So, how do we multiply numbers in binary expansion? We have to learn how to do that. Okay. Tell me when to stop. Tell me 3 minutes before I need to stop. Okay, so how do we multiply numbers in binary expansion? Well, you write y as the sum of 2 to minus sk. Remember that Sk was the place where your number y has a digit 1. So this is your y. And thus x times y is the sum x times 2 minus sk. But what is x times 2? Okay, so here is our number y. Remember, it was b1, b1 bar, b3, b4 bar, and so on. What I skipped writing is the upper index. Okay, but the upper index in this figure is 3. Then you have to shift your y by s1. S0 is 1, so you copy your guy. And then you shift by 2 digits to the right. So here is shifted by 2 digits. Then you have to shift by S2, which is 8 digits. So you shift it by 8. And then again by 2. So with respect to 8, you go to 10. So you repeat these two guys shifted by 8. And then you have to shift by 2048, which on this figure is this distance here. Of course, it's much smaller than in reality, but I want something to be seen on the screen. And then you repeat the whole story again, because you have this finite sums. So you have to know how to add these guys together. And notice that if you look at the row 1 and 5, they are shifted exactly by n3. Which is 2048. And if you look at the row 2 and 6, again, they're shifted by n3, and so on. So we rearrange the rows like this: the row number 1 and number 5, 2 and 6, 3 and 7, 4 and 8. And now this pair of rows is aligned. And you have to add B2 to B1. And then you have to add B3 to B2, B4 to B3. And the same will happen in this pair of blocks, and the same here and the same here. Now remember that these pair of blocks are almost mirrors. So there is a small lemma about what can be the result of adding almost mirrors B. Well, this is going to be either, if they are perfect mirrors, you have either zeros or ones. If they are almost mirrors, there will be a kick, a switch in one place, or maybe in two places. Sometimes you have 1, 1, 1, 1, 1, 0, and then 1, 1, 1, 1, 1 again. So at most you have 2 switches. But basically, these are almost constant. They are constant on very long portions. The sum of these two blocks, and the same here, and the same here and here. And then the whole thing, these 8 blocks together, is the sum of 4 blocks slightly shifted. So there will be some irregularity on this small section from this place to this place. You don't know what happens here, but inside from here to up to here somewhere, you know that you are adding 4 blocks which have very few switches. So the whole thing has also very few switches, maybe 4 times as many. But compared to the length of the portion, where you know how many switches you have, this is very few switches. So you realize at the end that your infinite sum will be dominated by long blocks without any switches. The frequency of switches is 0. And if the frequency of switching is 0, your block is determined, your sequence is deterministic. That's very, very easy. So this is basically the idea behind the group, behind this example. Okay. So now a result which we got from that result, from that example, we can create another example of something which is, in my opinion, even more fascinating. Namely, that you can take 2 deterministic numbers, multiply them, and get a normal number. And here is how you get it. So the theorem is there exists a pair of deterministic numbers, now I call them A and B, such that AB is normal in base group. And I'm sure this you can do it for any base, but we did it for base. Okay. So you take your number y from the previous example. That was the characteristic function of the set of finite sums of the sequence K. And you invert it. You calculate 1 over 1. You can do it in two ways, algebraically or graphically, combinatorially. In both ways, you can actually compute what it is. And if you compute what it is, you can prove that it is deterministic. And this is a big mystery, and we have an open question associated with this phenomenon, which I will state on my last slide. I will formulate all the questions. So if you take the inverse of that y, it is also deterministic. And that's it. Because now you take A to be xy. Remember from the previous example, xy was deterministic. xy was the sequence that had density of switches 0. And you take B to be 1 over y, which is the inverse of our deterministic number, which we can prove is deterministic. So they are both deterministic. And the product AB is x times y times 1 over y, which is x. And remember, we started with x being normal. So that's it. This is the example. And I think it's fascinating that you can take two sequences which are deterministic. That means they have, in some sense, entropy 0. So they reveal no chaotic behavior, nothing random there, right? They are completely predictable, knowing that the future, you know the past. And you just multiply them algebraically, which is some sort of combinatorial procedure, because I just showed you how to multiply numbers in binary expansion. You just shift one of them by the digits of the other one, and you add them. And yet you can create something normal, which has full entropy. So in some sense, this even resembles a little bit of Chaulas conjecture, where you have a sequence or a function on natural numbers, which depends on the number of divisors. So you can think of this as being some deterministic procedure defined function. Because what is it? You take the multiples of 2 and you put minus 1 at each multiple of 2. Then you take multiples of 3 and you put minus 1. And you multiply these two ordinateless. And you proceed like this infinitely many times. And the conjecture is that you will get something normal. That's Chaulas conjecture. So this example, of course, is far from deciding about Chaulas conjecture, but it shows that it is possible from very simple deterministic numbers to create a normal number by using multiplicativity. And of course, usual function or the value function are examples of multiplicative functions. So the multiplication here is somehow in play. So I think this is very interesting, but actually simple for combinatorially. It wasn't very hard. It is only a little tedious to do the details, but conceptually it's not very deep.
But I think try to interpret it in Rauzy's interpretation with the codes. Do you see how it fails? Because what you said, right, it seems like you convinced that it shouldn't happen, right? But it does happen. So what happens then?
Well, we don't completely understand because multiplication is not a finite block code. It's not like addition. Addition is also not a finite block code because addition has the carry, and the carry sometimes can go from very far away. So you have no finite horizon of it is fine. But multiplication, there is no such situation, but it does not commute with a shift or with a multiplication by 2 modulo 1. So we don't know really what is. We are just discovering some new phenomenon. We have yet to try to better understand what's behind it. The way to understand is to ask questions. Here is a number of open questions. Then well, the initial comment is that normal points form a set of full measure. So if you shift one of the sets, so you take a set of normal numbers plus some other number. These two sets, the normal numbers and the shifted normal numbers, they intersect. So that means that you can represent any number as a sum, also as a product. The same is with product ratio of two normal numbers. So taking product sums ratios of normal numbers, you can get anything. But deterministic numbers are small in both senses. Topologically, they are meager set. Measure theoretically, they are zero measures. So you cannot argue like this. So the following question arises. First question is related to this phenomenon of y and 1 over y being normal. Is it a rule or is it coincidence? Is the inverse of a non-zero deterministic number always deterministic? I don't think it is true, but we failed to prove it in general. We can only do it for this one example. And the symmetric question is the inverse of a normal number always normal, 1 over x. No idea so far. This could be true, but is it true? I don't know. And a specific case of these two questions is there a pairs of mutually inverse numbers, one being normal, the other one being deterministic? Is there a pair of such numbers? That would, of course, settle both questions. That would settle both these questions in the negative. And it would be the most extreme case. And we believe this should be possible, but on the other hand, as this example with multiplying two deterministic numbers to produce a normal number, it suggests that maybe you need to combine at least two deterministic numbers by multiplication. And taking inverse involves just one number. So if you take the inverse of just one number, maybe that's not enough of chaos built in to create normality. But this is all, speculation. We have no actual idea. Now, similarly to this thing here, can any non-zero real number be represented as the product or ratio of two deterministic numbers? Here, the sum is excluded, of course, because sum or difference of deterministic is deterministic. But by multiplying, we know that you can get a normal number, for example. Can any number be obtained this way? No idea. Can any non-zero number be represented as a product of a normal and deterministic? So this is a relaxation of this previous question. We know that two normal give you anything. We don't know about two deterministic, but maybe easier is a mixed situation. You take one normal, one deterministic, you want to create everything. No idea. Okay. Now there is another question related to normality preservation by addition. We know that rational numbers, sorry, I said by addition. This is not what I wanted to say. Sorry, by multiplication. We know that rational numbers have this property that they preserve normality by multiplication. We know that deterministic numbers not necessarily have this property. Are there any irrational numbers with that property that they preserve normality by multiplication? No idea. How large would that set be? No idea. And similar question, are there any irrational numbers with that property? Now I call them B, like the base. So this should be something else. This is not the base. Such that they preserve determinism by multiplication. Maybe these sets are the same sets. No idea. Maybe these are just rational numbers and nothing else. No idea. So this is a sequence, a list of open problems which maybe are worth thinking about. or maybe they are not worth. It depends on your attitude. We find them very, very interesting, and we're curious about, especially this. This would be something very, very strange. But we don't. Okay, so this is it. Thank you very much.
Or are there any questions, offline and online? Yes, please.
So you have defined this upper and lower entropy of the point, which is a kind of approach between determinism, you know, the size of points with the given or bounded the upper or lower entropy.
It seems that because you have residual set, no, you have full measure set of full Lebesgue measure set of normal points. All the other categories are of measure 0.
So naturally dimensions.
And then dimension, yes, that should be also 0. But as far as residuality is concerned, so again, all points which are not normal, this is a residual set. But deterministic in that set are meager, and I think every category again alone should be meager. So topologically, these are all small sets, probably. You have to take all non-deterministic, so positive, no, less than log 2 upper end.
Dimensional entropy are related notions.
Sure. And also you have to be careful about one thing, namely this lower and upper entropy. This is not the entropy of the orbit closure of it. That's clear, but it's easy to confuse. The orbit, for example, the Möbius function. If you take the Möbius function, it has it generates only the Mirsky measure of entropy 0, but the orbit closure has full entropy. Or no, it has entropy something with pi/6.
Yes.
Right, but it's positive. So this is a different can be. We have a notion of a strictly deterministic point. That's a point whose orbit closure is deterministic or has entropy 0. It's a stronger notion. And we also have some results for amenable group action, but then of course you don't know what it means to add 2 numbers, because that's a different story. You have to find some other terminology to deal with that, but it's also interesting what happens for the experiment and so on. And these are also interesting considerations. Lot of different flavors.
Any other questions?
So internet, no.
Yeah. In your example, the deterministic number y is very special, as you said, and maybe 2 regular, 2 deterministic.
Yeah.
So maybe should you distinguish levels of deterministic?
Yes, and the only tool that we think we have is complexity. It's how to do. But it has to be complexity again. It is not the topological complexity where you count how many logs of the different strength you have, because that would be again the entropy of your closure, or the complexity of your closure. You have to look at the complexity counted from the beginning in some sense. We have such a notion, and yes, you can.
Well, some people play with lower entropy. I mean, polynomial, or I don't know.
Right. So yes, we can. Yeah. This example is linear. Right, but it's natural to expect that if you have very low entropy, then this number should maybe preserve normality by multiplication, like rational numbers. They have linear complexity because they represent periodicity. And this example has very low entropy and it does not preserve normality. So what else to search? Higher complexity? No, that's the opposite to what you would expect. So yeah, this is the reason why I was emphasizing this very low complexity. Okay.
I see that. Is there a question in the chat? Yep.
Yeah, sorry. Can you hear me?
Yes.
Oh, perfect. So I asked myself, this notion of lower and upper entropy of a point. I mean, like the usual notion of entropy of a measure doesn't depend on the choice of a Fellner sequence, right? But the genericity might depend on the Fellner sequence. So I asked myself, is this notion then independent of the choice of the Fellner sequence?
No, this notion is definitely dependent on the choice of the Fellner sequence.
Okay.
Because for instance, if you take a sequence which has different lower entropy, you have a lower entropy in N. So it definitely depends on the Fellner sequence.
Okay, let's try with Tomasz again. And we have the